Namaste, warm greetings to one and all present here. I, Dr. Smriti Shukla, and along with Ms. Richa Parhar, on behalf of Amity University, extend a warm welcome to all the esteemed dignitaries, panelists, and the attendees present at this platform. Today, with the blessings of Honorable Founder President Dr. Ashok K. Chauhan sir, Additional President and Chancellor Dr. Asim Chauhan sir, we are honored to welcome you all. With the dynamic leadership of our Vice Chancellor Professor Balwinder Shukla and Group Vice Chancellor Professor Gurinder Singh, and we are honored to welcome you all at the virtual deliberation on Ozone Day Celebration 2023 under the aegis of Global Warming and Climate Change Cluster. Ladies and gentlemen, moving ahead with beautiful thought, पिंड दहन का सूर्य शौर में ज्वाला बनकर जलता है, कुछ पराबैंगनी हानिकारक किरणें उत्सर्जित करता है। ओजोन परत सीमा ऐसी जिसे पराबैंगनी भेद न पाए, धन्य व शीतल गोला है जो धरा पृथ्वी मां कहलाए। ओजोन क्षरण की वजह सीएफसी, हेलॉन्स, टीसी का तैश है। जब ओजोन छिद्र हो जाएगा, स्वस्थ रहेंगे तब न लोग। एसी, फ्रिज, इलेक्ट्रॉनिक से निकली ये विषैली गैस है। जब फिर फैले त्वचा, कर्क, चर्म और नेत्र के भयानक रोग। तापमान भी खूब बढ़ चुका है, मौसम हमसे रूठ गए हैं। बरखा होगी आज या कल, किसान की आस टूट गए। मोर, चकोर, पपीहा, सोन, चिड़ैया ना गौरैया अब गाती है। तरुओं की हुई गोद है सूनी, अब कोयल ना इटलाती है। वन जंगल पयोधर सूख चुके, ना अनाज है ना पानी है। कितनी नस्लें हैं विलुप्त हुई, बाकी भी अब हो जानी। पेड़ पल्लव टूट, बेलड़ी, झाड़ियां आज सभी कटते हैं। अपने अपने रुतबे के माफिक रुपए ऊपर तक बढ़ते हैं। संतुलन सौर का है बिगड़ रहा, जो ये प्रदूषण है बढ़ रहा। मानव अपनी मूर्खता को आज दूसरों के सर मढ़ रहा। 16 सितंबर ओजोन दिवस पर चलो हम शपथ उठाएं, प्रदूषण को जड़ से मिटाने का हम बीड़ा उठाएं। ओजोन क्षरण का विषय आज विचारणीय, चिंतनीय है। गर सचेत हुए न हम, अभी तो विनाश दिशा में अग्रणी है। Ozone is the blanket that is protecting us all, and World Ozone Day is a reminder that it is time to protect that blanket. With this thought, I feel elated to invite Professor Tanu Jindal, Director, Amity Institute of Environmental Toxicology, Safety and Management, to enlighten us about the theme and idea behind today's deliberation. Professor Jindal is a renowned environmentalist, educationist, and scientist with over 25 years of experience. She has completed 12 projects and 9 patents with various national and international funding in Antarctica, ocean, river, and groundwater, air, land pollution, and toxicology studies. She and her student have been awarded many times from American Chemical Society meetings. She has traveled extensively across the globe, presenting over 120 papers in prestigious conferences. She has several publications in refereed journals and 4 books to her credit. She is fellow of National Environmental Science Academy and has been conferred Scientist and Environmentalist Award. Professor Jindal is Green Ambassador and follows passion of protecting planet through environmental education and research. She is contributing towards R&D in all campuses of Amity. Welcome, madam. Over to you, ma'am.
Yeah. So I welcome all my worthy speakers of the day. And we have Professor Umesh Kurshesh. I welcome you, Professor Umesh. I welcome Rolly Costumo, and I also welcome Dr. Akinender. I also welcome Dr. K.V. George. With the blessings of Honorable Founder President, Dr. Ashok K. Chauhan, we have been celebrating various environment days at MIT University. Ozone Day is one of the very important day which has been celebrated every year, and with the dynamic leadership of Professor Balwinder Shukla and Dr. Atul K. Chauhan, we are our Chancellor. We are delighted to be here, and now this time the theme of this Ozone Day is Montreal Protocol, fixing the ozone layer and reducing climate change. So on the theme we have kept this session, and I am grateful to honorable speakers that they have agreed in such for such important day. I will share my thoughts about Ozone Day, and I'm sharing my slides. Can you see the screen now?
Yes, ma'am.
Okay. So as I said, that the Ozone Day theme is Montreal Protocol, fixing the ozone layer and reducing climate change. Why is the ozone hole getting smaller? This is a good news, and scientists say the Antarctic ozone hole is on the road to recovery. After the Montreal Protocol, ozone had stopped growing in late 90s because of the 1987 Montreal Protocol. You can see the graph, ozone is declining. This ozone hole, you can see that ozone hole has slightly improved. It was very bigger here, and now you can see that it has been decreasing and it has shrunk to certain extent. 9.3 million square miles. This is the area of this ozone hole, and it is the area roughly the size of North America. In fact, there is more ozone in the warmer temperature, and while there is less ozone in the colder temperatures. Now, what is the reason of this ozone hole? There is environmental pollution because CFCs and O3 depleting substances. There is alteration in stratospheric chemistry, depletion of stratospheric ozone above Antarctica and the Arctic, and human health is been affected because of the release of UV radiation to the atmosphere. Human health is affected, ecosystem is affected, materials, air quality. All things are being affected because of the UVB radiation. I will just explain little about this and looking forward to hear from the worthy speakers. The stratospheric ozone depletion causes climate change, and this further causes accumulation of acid aerosols. Increased UV radiation at the Earth's surface, photochemical formation of tropospheric ozone also happens. Now, together this acid aerosols, they causes crop and forest damage, human respiratory illness. And with photochemical and increased UV radiation at this of ozone, both impact direct human health and damage materials like plastic, paint, rubber, etc. Even there is a reduction in plankton and fish populations, reduced crop yields, stunted plant growth, and there are more skin cancers, suppression of immunity, more cataract and blindness, and more infectious diseases, less effective vaccination. Now, this is the flow chart for the same. Ozone depletion causes UVB radiation percolation at the Earth's surface, causing global warming. And this further is the climate change because of this glacier melting in polar regions. Droughts, floods are been happening, as you know, they are very frequent nowadays, and disruption of water cycle. Entire ecosystem is altered, change in distribution of plant and animal species, and decrease of biodiversity in coastal lands. UV-induced allergy. In fact, this occurs in 5 to 20% of the population, often after first spring summer exposure to UV radiation. As I said, ozone is more in the warmer climate, and it increases photosensitivity of the skin, temperature, dust, deserts. I have taken to show the impacts of ozone as other speakers are not speaking about it, but it is very necessary to know the adverse impacts of ozone. Higher temperatures may lead to more skin cancers for the same UV exposure. For every 10 degrees Celsius increase, there is an estimated 3 to 6% increase in skin cancer. Further, malignant melanoma, non-melanocytic skin cancer, basal cell, carcinoma, squamous cell carcinoma, sunburn, chronic sun damage, and photodermatosis may happen because of exposure to UVB radiation. There are also drastic impact over the eye, acute photokeratitis and photoconjunctivitis, climatic droplet keratopathy, pterygium, cancer of the cornea and conjunctiva, lens opacity, cortical posterior subcapsular, uveal melanoma, acute solar retinopathy, and macular degeneration. These are also some of the adverse impacts of ozone and UVB radiation. There is further impact on immunity and infection. Suppression of cell-mediated immunity, increased susceptibility to infection, impairment of prophylactic immunization, and activation of latent virus infection, increase in certain infectious diseases like malaria, Lyme also happens. In fact, because of the UVB radiation exposure and ozone, there may be altered general well-being, sleep-wake cycle, seasonal affective disorder, and mood disorders. It has been seen that terrestrial ecosystem is also affected. Plant growth has found to be reduced by 6% in response to increased UV radiation in areas of significant ozone depletion. Growth reduction are due to direct damage plus diversion of plant resources towards protection and repair. In fact, green pigment is used for energy capture and growth. Therefore, because of this loss of green pigment, there is reduced growth. In fact, aquatic ecosystem is also affected. Changes in climate and UV are expected to in many areas. Aquatic organisms will be exposed to increased UV radiation, increase the degradation of dissolved organic matter, making it less available for phytoplanktons. Because of increase in CO2, there is increase in acidity, low pH occurs, and decreases the skeletal formation of the shells in calcified organisms. Ozone depletion over India. With so much worry about rapid ozone depletion taking place in various parts of the earth, Indian scientists are closely monitoring the ozone layer over India for possible depletion trends. Since India already receives high doses of ultraviolet radiation and is at the threshold, effects of ozone layer depletion could be far more disastrous in India. While there is no trend in the total ozone value, there is some evidence of the ozone depletion at higher altitudes at about 30 to 40 km, even over the tropics. Even a slight depletion of the ozone layer over India may lead to large percentage changes in UVB radiation, as told by many skin specialists in New Delhi, that the incidence of skin cancer in India is low. But they admit that the survey conducted to identify any trends are inadequate. The controlled studies to observe the effects of changing UVB radiation concentration on crops are on. What are the possible solutions? The possible solutions are reduce the production of those chemicals that cause the destruction of ozone, namely CFCs, freon, and nitrogen oxides. So in fact, new refrigerators and new appliances are coming without CFCs and other new technology. Then proper recycling, staying out of the sun using sunscreen, increasing carbon tax, carbon cap and trade, which gives a maximum number of how much carbon a country can emit, and also carbon sequestration. This is the uh, spatiotemporal variation of surface ozone and its precursors, and the impact of anthropogenic effects on ozone buildup over the major states along the Ganga River. So this is the research being conducted by one of the PhD scholar, Priyanka Sinha, and she has taken Jharkhand, Bihar, and West Bengal for this. You can see the data has been taken from 39 AAQMS stations in New Delhi region under the CPCB DPCC IMD network. Spatial variation of ozone, NO, NO2, and CO. Temporal variation of ozone and its precursors, and regional photochemical O3 buildup due to large-scale anthropogenic sources using residence time analysis. You can see the concentration of ozone rises between 6 a.m. to 6 p.m. and it is at peak between 12 to 2 p.m. Now this is also spatial variation ozone over New Delhi by GS based interpolation technique. You can see that ozone is more in industrial area near Faridabad, and also ozone is more in Anand Vihar area, like there is more traffic. So in where the more pollution is there, ozone concentration has been found more in those areas. So I end this, and I'm looking forward to hear to our worthy speakers. Protect ozone layer, save Earth to bring work for the new Earth. Thank you so much.
Thank you, ma'am.
Yeah, there is no safe. In fact, there is no safe life zone without ozone. Let us act as a whole to prevent ozone hole. Thank you.
Thank you, ma'am, for addressing the platform and sharing the insights into the theme for today. Over to you, Richa. Miss Richa, are you there? Over to you.
Thank you, ma'am. Thank you, ma'am. Kindly share the curtain raise the Miss Yogita. Earth without the ozone layer is like a horse without a roof. Save the ozone layer. Let's take an oath to protect the ozone layer and save life on Earth on this World Ozone Day. Moving ahead, now I would like to invite our next speaker, Dr. K.V. George sir. Sir has completed his BE in Civil Engineering and ME in Environmental Engineering from Government Engineering College, Jabalpur, and PhD from IIT Delhi. Currently, Sir is working as Chief Scientist and Head Air Pollution Control Division of National Environmental Engineering Research Institute, CSIR, NEERI, Nagpur. Sir has 32 years of work experience in environmental engineering. Sir has worked for cleaning studies of Union Carbide India Limited, Bhopal, after the MIC gas accident and worked on restoration at Visakhapatnam due to gas leak during lockdown period. He has carried out environmental impact assessment studies for chemical industries, thermal power plant, etc. Presently conducting air pollution related studies for different cities in India and abroad. Sir has done international projects on air quality study at Ras Laffan Industrial City, Doha, Qatar. Welcome, sir.
Am I audible?
Yes, sir.
Okay, thank you, Richa madam. Should I upload now?
Yes, sir, please.
Is it visible
Yes, sir.
and is it moving?
Yes, sir, it is moving.
Okay, thank you. So,
Thank
good
you, sir.
afternoon to all the uh, invited speakers, faculty of Amity University, students. I was asked to make a presentation on this topic, the theme Montreal Protocol. So it was discussed and decided that since there may be a large number of students, audience, who are not very much exposed to this topic because academically they need not cover it. So I was asked to give a basic introduction of the ozone related issues, how it is formed in troposphere, stratosphere, its formation, destruction mechanism, and a brief introduction where thereafter the advanced talks will help them understand. So I will be speaking on the introduction to Earth's ozone layer, natural formation, and anthropogenic destruction. So prior to that, I would like to begin with my institute, working in CSIR NEERI, Nagpur, Council of Scientific and Industrial Research. He's having 29 laboratories, and they are in different fields: biological science, chemical science, engineering science, information science, physical science. Among engineering science, there are 10 laboratories, and one of them is National Environmental Engineering Research Institute. It started sometime 60 years ago, 1958. At that time, its name was CPERI, Central Public Health Engineering Research Institute, which was later renamed as National Environmental Engineering Research Institute in 1974 by our late Prime Minister Srimati Indira Gandhi. Now, let me come to today's topic. All the students, my address is mostly to students who are not exposed to this subject. So for them, if they want to know about ozone, what they should know initially is the atmosphere. So I feel this is the sort of syllabus that the students should know: how Earth is formed, how the atmosphere evolved, their seasons, winds, how oxygen is formed, and followed by ozone layer, then its depletion, identification, detection of ozone hole formation, etc. To understand formation of Earth, Big Bang theory, most of us have learned in 9th standard. Today, everyone knows it since 9th standard. These are all some of the pictorial representation. Some 10 to 20 billion years ago, a very big number, when some Big Bang happened. It was proved that there was a Big Bang by two scientists, Arno Penzias and Robert Wilson, when they discovered some cosmic ray reaching Earth's surface, and that cosmic ray was released during the Big Bang, when the Big Bang event happened. They earned Nobel Prize in 1978 for their discovery. So these are all some of the pictures to show how Big Bang took place: formation of sun and Earth. This is the formation of sun. Why it is glowing? It is emitting radiation. These are all our star, and followed by our graha, upgraha. So here you can see we are standing on Earth. This is the location, and you can see the size also. Now, distance, radius of Earth. Now, recently Mangalyaan, so you are all familiar with these concepts very clearly. Then, so when Earth got formed, gradually, so there was first level of atmosphere, and after its cooling, the depressions were filled with water, and this is what it looks like today. But what was the first atmosphere? Because that first atmosphere will lead us, understanding will lead us to know how oxygen came, then followed by how ozone came. So what is the atmosphere here? Envelope of gases that surrounds the Earth. And the first atmosphere, when it was formed, probably it was hydrogen and helium, which are light weight gases. Most of them lost in the early history because of the Earth's gravity was not able to hold it. Then second atmosphere, so when Earth starts getting cool down at the top, the subsurface volcanic eruption started taking place, and gases again started evolving. But at that stage, there was no free oxygen, because free oxygen is not found in volcanic gases. At high temperature, this reacts and forms oxides. Now the question comes, how oxygen started coming on the Earth. There are two mechanisms. One is photochemical dissociation, other is photosynthesis. So let's think of photochemical dissociation. This is breakup of water molecule by ultraviolet radiation. Now, till this stage, we are not talking about ozone layer. So there was no ozone in the beginning. All ultraviolet radiation and all very short wavelength radiation, they reached up to the Earth's surface, and they caused split of water molecule releasing oxygen. That oxygen again got split into nascent oxygen, thereby forming ozone. At first level, ozone was formed at the surface of the Earth near ocean. Gradually, when its concentration started building up, the layer thickness started growing up. This ozone prohibited entry of short wavelength towards the Earth's surface. So gradually, ozone layer was getting built up at a higher elevation because short wavelength was not able to penetrate this ozone layer, and it did not allow formation of further ozone at the ground surface. So this is what is the first photochemical dissociation by which oxygen started forming. So this is at the stratosphere means once the ozone layer formed, or while it was being developed, the radiation H nu, it split oxygen into two atoms which reacted with ozone, oxygen and formed ozone. So this is the production, then destruction. Ozone got destroyed by another wavelength, which is about 336 nanometers. So this is the formation and destruction of ozone at the top of the Earth's surface in the atmosphere. And this is called Sir Sidney Chapman reaction. Now, the ultraviolet rays. So what reaches today's Earth is visible radiation having 400 to 700 nanometer wavelength. And before the violet color, there are three, it is divided as ultraviolet A, B, C. You can see ultraviolet C doesn't penetrate through this ozone layer, whereas B partially enters, A, about 95% it enters into the Earth's surface. Then the second phase is once Earth's surface is protected by the formation of ozone, the life started. And when the life started, now there are different theories. Either if we go by religious roots, there are one philosophy. If we go by the scientific theory, there's another philosophy by which we say how life started on Earth. So when life started, there at that stage, the photosynthesis was the second step by which oxygen started building up at the lower atmosphere, near our Earth's surface. So carbon dioxide, water molecule, in the presence of sunlight, which is not ultraviolet, this forms organic compound, hydrocarbon and oxygen. So now oxygen is getting built up at the surface of the Earth, and ozone is at the higher level. Here you can see these are some of the numbers. One need not mug up the students. Just realize visible wavelength 400 to 700 nanometer, then UVA, B, C, and all these things. You will get it in literature. And you can see this is diagram something which the students who are interested in this subject should be very much familiar with and should learn the visible wavelength, what is entering towards the Earth's surface, and what is prohibited by the ozone layer. This is the sun's radiation. This is the return radiation by Earth. How it behaves, you can see sun's radiation, shortwave solar radiation comes up to the surface of the Earth. And after losing its heat energy, the return radiation, which is higher wavelength, doesn't have much energy to move out of the Earth and therefore keeps the Earth warmer. So this is what is the phenomenon. Now here you can see oxygen level over the x-axis is time, historical time. Y-axis is oxygen. So gradually oxygen level started building up, and today we are at this level. So this is our today's atmosphere. So these are all school syllabus, but I'm just referring. This diagram, which is called atmospheric window. So different gases. From top you can see N2O, which is a greenhouse gas, ozone, oxygen, carbon dioxide, water molecule. And the lowermost is atmosphere comprising all these. Here you can see this white space. These are the spaces where the x-axis you can see wavelengths of radiation. This gas can penetrate through these gases. So let's take the example of, say here, ozone and oxygen. This allows all this blank space. You can see this much size of radiation is allowed to enter towards Earth's surface. But here you can see a very small band, 185 to 210 nanometer. Only 10% of the radiation is allowed to come towards Earth's surface. This is something which can cause health impacts. So this is a very small window, but one needs to be careful. Now, where the stratospheric ozone, so Earth atmosphere is divided into troposphere, stratosphere, mesosphere, thermosphere, vertically if you go up. Where is ozone layer? It's not a thin sheet. Here you can see something like 10 to 50 kilometer height. Ozone layer is spread. If someone says, what is the thickness of ozone layer? Yes, it is about 40 kilometer thick. And the central portion, you can see it is higher density and it's gradually varying towards upper and lower section. So this is where the ozone is found. Now some interesting facts. How to measure it? So in 1920s, GMB Dobson developed a spectrometer that could measure small concentrations of ozone. How to, what is the unit in his memory? This is named as Dobson unit. Now, the concentration is different along this line, vertical depth or in the atmosphere. Now, if that vertical column of ozone is brought to the surface of the Earth at the sea level, what will happen? It will be subjected to higher pressure. Because of that higher pressure, the ozone layer will squeeze. Now you can see if the vertical column of ozone is brought to surface atmosphere at 0 degrees Celsius, its thickness will be merely 3 millimeter. And this is considered equal to 300 Dobson unit. So 1 millimeter is 100 Dobson unit in the memory of Dr. GMB Dobson. Now what is ozone here? We call ozone hole if the Dobson unit in any portion is less than 100 dB. Okay, so this is the beginning, how we have detected how to quantify ozone hole. Now this is regarding ozone. It was, I should say, identified by a German scientist, Christian Friedrich Schonbein in 1839. It has got some theory regarding effect of tropospheric ozone. Professor Tanu Jindal has explained it at much better length. You can quote two examples. One, you can see at our surface level, the curling of leaves. This is one of the phenomena. This happens in the presence of ozone. This is one of the effects. Another effect is cracking of rubber. And if I can recall in my school days, my cycle tire never got cracked. But today I see the cycle tires got cracked. And what is, they are rubber molecule, which is a long chain hydrocarbon. If ozone is present, it can break those long chain compound, and therefore the rubber shows crack. So that's an indication of presence of ozone. It also reacts with the paint or all our old murals, and it disintegrates because it's a strong oxidizing agent. Ozone is not welcome at the ground level, surface level, but it is very much needed at the higher elevation. Now, these are some of the vertical scale, not scale, layers of atmosphere. Here, something for academic interest. There's a line. Suppose here you can see bottom of the surface of Earth. Mount Everest, something 8.4 kilometer. A plane flies below 20 kilometers. Then there is a line at 100 kilometer, Karman line, Bohm Karman line in his memory, K line. So this is a 100-kilometer line. All aeronautics related work goes here, below 100 kilometer, and astronautics above 100 kilometer, only for academic interest. So these are the layers. You can see these thicknesses. Now, how ozone is destroyed in the stratosphere, the upper level of atmosphere. So there are several theories. First of all, we need to detect whether there is an ozone hole or not. Second thing, what can cause its destruction? So there are certain theories. The chlorofluorocarbon, which we release, that reached up to the surface of the, not the upper layer of ozone, and then it reacted and destroyed ozone. The question comes, and that should come very naturally, is when these molecules were moving up, why it didn't get destroyed here itself in the atmosphere? Okay, so let us see. One of the set of chemical is chlorofluorocarbon. Here I'm giving an example, CCl3F, one of the freon gas. This is having a property of very high stability. So when this was discovered or synthesized sometimes in 1939, I'll show in the next slide, it is there. It was very much appreciated. Prior to that, sulfur dioxide, ammonia was the coolant. Thereafter, CFC was synthesized and considered as one of the very good chemical to be used as coolant because it has the property of very good compression from gas to liquid, and that's what is used in refrigerator and air conditioner because that works in the principle of this adiabatic expansion, abstraction of heat, etc. So here you can see a chlorine atom is attached to this CFC. Now this molecule CCl3F, there is no force at the surface of the earth that can destroy this molecule. So this was free to travel high in the atmosphere and it reached our ozone layer. There it encounters, you can see this H nu. This is actually shortwave solar radiation. This ultraviolet C, this radiation is not available at the surface of the earth. This is available at the ozone layer. What it did, it split into chlorine atom and CCl2. This chlorine atom is the responsible person for a molecule or atom which for destruction of ozone. You can see the subsequent reaction. The Cl plus O3, this releases oxygen. Again, this ClO reacts with nascent oxygen, which was supposed to form ozone, and again it forms oxygen, and again a Cl chlorine atom is released. So this is what exactly is happening. We are releasing chlorine associated with chlorine and carbon, which is a very stable compound, and it reached the surface of the at the higher altitude. Now, ozone at two levels, troposphere and stratosphere, needs to be understood. Its impact, formation, destruction separately. In troposphere means at our level, where we are standing, is formed by NOx chemistry, by CO, VOC chemistry. It's a altogether different subject. Then it is formed at stratosphere by UV rays. It's depleted by NOx from the supersonic jet plane and by chlorofluorocarbon. There are two mechanisms. All these things are given, they're identified by these scientists. Chapman reaction, Paul Crutzen, and Roland and Molina. Now, here, as I told in 2 slides prior to this, 1928, yes, the correct year is 1928, Thomas Medley from DuPont, a chemical company, they synthesized chlorofluorocarbon, a set of these species, chemical molecules called freon. Their property is they are non-toxic, non-corrosive, non-flammable, chemically inert. And because of these properties, this molecule was able to reach up to the ozone level. Okay. Now comes the second phase of this study. How chlorofluorocarbon measurement started. So there was one scientist named James Lovelock. He developed an electron capture detector which monitors CFC in the ambient air in 1970. So this is something very interesting how it moves. And this instrument was able to detect very small concentrations. So he's found that atmosphere concentration of about 60 parts per trillion. We talk of millions. Higher level studies goes to billions. But this electron capture detector was able to reach up to trillion. So he found that CFC11 in the atmosphere of 60 ppt. So this was his experiment when he allowed his instrument to be deployed on one of the ships which moved from London to North Atlantic. Then he wanted to conduct this experiment towards Antarctic. So he requested for some funding from the British government so that his instrument can be set on a ship that moves towards Antarctic for expedition. But his request was rejected by the government, saying that it will generate some data, that's all. But he had something in his mind. So James Lovelock used his own money and in a research at Shackleton in 71, he set up his electron capture detector. And 2 years later, he reported that this detector was able to found CFC in every one of more than 50 air samples collected up to Atlantic Ocean, towards Antarctic continent. So this was the first discovery of presence of CFC. Now, prior to this, we were happy that CFC is a good refrigerant, coolant, but here it is found that just because of its property of being stable, it is persistent in the atmosphere. Then, subsequent to it, to some scientists, Sherwood Rowland, Mario Molina, they found this experiment and then it hit them. But if these chemicals are persistent in the atmosphere, where they are going, how they are getting reacted. So its ultimate uh, destiny is higher in the atmosphere because of its stability and how it will react at the higher atmosphere. They found, first of all, why it is not getting reacted or what are the modes by which chlorofluorocarbon or any stable gas is reacted at the lower atmosphere, photolysis, dissolution in water, or with any reaction with hydroxyl or ozone. But nothing was happening with CFC. So they found that yes, it can go up to ozone layer. What will happen? They did some literature study. Now, here is the research part. They just did some literature study and they said that there is a possibility that it will react with ozone. But to what extent it can react with ozone, that it will become a global phenomenon, global effect. They found a single chlorine atom can remove as many as 100,000 molecules of ozone. This is a very big number. Then some estimates came how much CFC is produced on Earth by different countries, different plant factories. What is their life cycle? Life cycle means usage cycle, and thereafter everything is released in some way or the other. There's no way to destroy it at lower atmosphere. So everything is getting accumulated at the ozone layer where it can damage our Earth. So here comes the next discovery, very scientific discovery. In Antarctic continent, India is having a station named Dakshin Congo 3, which was set up in 1983 under the leadership of our late Prime Minister Srimati Indira Gandhi. Another station, Maitri, 1989. Close to our station is Russian station Novoladrevskaya. Then there are other stations far away from our station, Vostok, McMurdo, Emerson Scott, and Halley Bay. Now, Halley Bay is the British station. What they found, you can see this is the concentration of ozone. Most of the countries, they were measuring ozone using this Dobson unit. They found that towards 1990s, the concentration of ozone thickness in the upper level is coming down. Now, initially, when this result was analyzed, they thought it is an outlier. So if you do statistical analysis of any data set, what you do is plus minus 3 sigma. Beyond that, everything is outlier. But in this particular case, something hit them that if it is an outlier, but how long? They found there must be some reason. But the data was just preserved as it is. Subsequently, Molina and Rowland, they found that their theory is matching with this reduction in ozone layer. Then they said CFC is responsible for destroying ozone, and they came out with their philosophy, their theory. So in 1974, Rowland and Molina made a disturbing prediction. They said if industry continued to release million tons of CFC into the atmosphere, the atmospheric ozone would eventually drop by 7 to 13. And all the three got Nobel Prize in 1995 for this particular discovery. So this is how we reach up to detecting the ozone hole. Now, this is some of the photographs which I was one of the members of Antarctic expedition, Millennium expedition year 2000. So these are the icebergs you can see. This is our station, Maitri, 26 January. Our function, which is joined by the German team also. This is you can see the balloon, which is released, which contains ozone sensor. So when it goes up, it sends the signal of ozone at different elevations. So this experiment is conducted by our station also, and India Meteorological Department is doing this experiment. This was our laboratory from experimental setup. Now, at lower level, about ozone, what we are finding today. Now, this is my last set of slides. During lockdown, what is the condition of atmospheric pollution? So I am presenting here the data of Nagpur. Very hard lockdown. Everything was stopped. This is for Nagpur data. You can see particulate matter 10, concentration was high before lockdown. And during lockdown, you can see the concentration came down with less fluctuation. X-axis is the time of the day. Y-axis is concentration in microgram per meter cube. So this is the PM10 level. This is PM 2.5. So during lockdown, the source of particulate matter came down. So it is low. Now, when I analyze for all the parameters, particulate matter 10, 2.5, NO2, SO2, ozone, CO, what I find is ozone is during lockdown is high compared to others. Whereas for other periods, you can see all other species during lockdown has come down. So a question that should come, why during lockdown ozone level in our cities has gone up? In not only in Nagpur, I did it for several cities and found that during lockdown, the ozone average concentration moved little high. So here is the answer. This is the diurnal variation of Nagpur ozone. This lower red color is the ozone level diurnal variation for 2 months when the city's functioning was normal. This blue color is during the lockdown period, 2 months hard lockdown. The ozone level at the lower atmosphere has gone up. The reason, at the same time, we also analyzed the presence of nitrogen oxide. So vehicular movement was less. Since vehicular movement was less, what vehicle emits is NO, 90% of NO and 10% of NO2. If vehicles are not moving, NO and NO2 is not present much in the atmosphere. Here you can see this blue color is the presence of nitrogen oxide in the atmosphere before lockdown. During lockdown, it has come down. This is responsible for titrating of the ozone levels. So since nitrogen oxide was not present in the atmosphere because of absence of vehicles, the ozone level increased. Now, it doesn't mean that in absence of vehicle, always ozone level will be high. Actually, if this lockdown is continued for a very long time, all ozone will be washed off and very small amount of ozone will be found. And the transboundary movement from one city to other, everything, or the ozone of previous day moving to other cities on the next day, that will also disappear. But for a short time, on 2 months time scale, this was the scenario. Ozone level increased during lockdown. So this is the chemistry. You can see NO at the lower atmospheric level. It reacts with ozone and forms clear oxygen. So this is how the ozone level increased at lower level. So this is all what I wanted to say as an introduction to ozone. And if you have any query, you can ask it now, or as per the procedure or whatever you have decided. Risha madam, you can intervene now and suggest how to go ahead. Should there be a question answer session? If so, or if it is at the end.
Sir, it is in the end, sir.
Okay, thank you. Thank you, ma'am. Thanks to all the participants.
Thank you so much, sir.
Yeah,
We want
Dr. George, you have analyzed certain, ozone trends over, I think, Arabian countries. You have
Yes,
analyzed
yes.
ozone. So
Yes.
if you would like to show certain those, ozone trends, I was expecting those. You showed me some ozone trends.
Okay, I have
Yes.
all those slides.
Yeah,
I'll,
because we wanted to see those areas, because how you have plotted through satellite and
just hold on, madam. Let me open another set of slides. I'll bring those slide also.
because you have done a very, when I went to Nagpur, you
Yeah.
have shown me very nice, slides wherein you have analyzed ozone trend.
Uh, uh, yes. Research my old slides. I have given it. Madam, if you permit me, let the other speakers continue. And by the end of it, I'll open those slides and show you how we have found the movement of ozone in the Middle East area. How from one country it moves to other country, and was
Yeah,
this.
that would be great. In fact, I was expecting that you will show those slides that, how
Madam,
ozone moves
you
from one
gave
place
me
to
half an
another.
hour's time, so I thought I should not.
No, no. Please,
uh,
please keep them ready and then maybe I
I'll
call
show.
you.
Yeah,
Thank you.
I'll show you. Let me search all those slides. And
Thank you so
yeah.
much.
Thank you, sir. We want to express our heartfelt gratitude for the incredibly enlightening session on this topic. Now, over to you, Dr. Smriti. Ma'am.
ऋचा आप ही बुला लीजिए डॉक्टर बंदोपाध्याय को.
Yes, sir. Now, I would like to invite Dr. D.K. Bandyopadhyay, Chief Advisor, FPO, and Chairman, Amity Law School and Amity School of Engineering and Technology, Chief Advisor and Mentor, Amity Institute of Environmental Sciences, Amity University in Uttar Pradesh, for sharing with us his view. Sir, we are most honored to have the privilege of hearing your kind words. Welcome, sir. Welcome, sir. Over to you, sir.
So thank you very much. Am I audible?
Yes, sir.
Just give me 1 minute.
Sure, sir. Sure, sir.
Hello.
Yes, ma'am. Again frozen.
रिचर्ड सर का पूरा प्रोफाइल पढ़ दो ना.
Yes,
So,
sir has started now.
I think I must congratulate Dr. Tonu Jindal. Are you able to read me, listen me?
Yes, yes, sir.
Yeah.
Yes, sir. Yes.
So I congratulate Dr. Tonu Jindal for taking this initiative as usual. She has been celebrating this Earth Day, Ozone Day, Environment Day for years. And this year also, it is not the exception that she has made it. And that is the way how we also get ourselves revived and reminded that yes, there is a beautiful ozone which can be either a boon or which can be a bane. I mean, this type of spirit, this type of understanding, I think all the time must be brought in us. Maybe during the last 1 year, we have forgotten it, but again, it has come over here. And it is so important that, Montreal Protocol, it keeps us our food and vaccine full. And they say that it is the world ozone, is to keep us our food and vaccines full. And that is the slogan that Montreal Protocol that gave. So for us, the most important thing is the tropospheric ozone, which has already just now been mentioned with chemical formula by my previous speaker. And it has shown that how stratospheric ozone are distinguishable from the tropospheric ozone. So the bad ozone, what we talk about is the tropospheric ozone, and which is nearest to the ground, and it is harmful pollutant which forms the sunlight, alters various chemical emitted by humans. And good ozones, on the other hand, forms by the stratosphere, the next higher layer where some jet planes fly. Ground level or bad ozone is not emitted directly into the air, but it is created by chemical reactions between oxides of nitrogen, or popularly known as NOx, and volatile organic compound in the presence of the sunlight. So sunlight actually works as a reagent, and in the presence of the sunlight, this reaction takes place. Now, stratospheric ozone is found in the stratosphere, the second layer of the Earth's atmosphere, 10 to 30 miles above the surface. Life could not exist without this protective ozone, which is also called the protective layer. The sun gives us light, heat, and other types of radiation. The ozone layer in the stratosphere absorbs a portion of the radiation from the sun, preventing it from reaching to the planet's surface. Most importantly, as mentioned by the previous speaker, it absorbs the portion of the ultraviolet light called ultraviolet B. Ultraviolet B is a kind of ultraviolet light from the sun or the sun lamps that has several harmful effects. Without the ozone layer in place, radiation from the sun would reach Earth directly, damaging the DNA of plants and animals, including the humans. The intensity of the sun's radiation could make photosynthesis, a process by which plants convert light energy into chemical energy to fuel their growth, becomes impossible. So such is the importance of this good ozone layer, which actually lying in the stratospheres, above the stratosphere. The 2020, very interesting fact, just if you look at, the ozone hole grew rapidly from mid-August and peaked at around 24.8 million square kilometers on 20th September 2020, spreading over most of the Antarctic continent. It was the largest, lasting as one of the largest and deepest holes since the ozone layer monitoring began 40 years ago. The ozone hole has developed because people have pulled the atmosphere with chemicals containing chlorine and bromide. So most important is chlorine and bromine. The primary chemicals involved are chlorofluorocarbons, every of us typically known as CFC, halogens, means halogens, and carbon tetrachloride. Once released from CFC, chlorine then reacts with ozone, O3, to form chlorine oxides and oxygen. Countries that are affected by it, most are Argentina, Chile, South Africa, New Zealand, and Australia. The largest ozone hole ever observed in the Antarctic was reported by NASA in September 2000, and the hole spread out over 28.3 million square miles, more than 3 times larger than the United States. The Montreal Protocol on substances that deplete the ozone layer, an international agreement made in 1987. It was designed to stop the production and import of the ozone depleting substances and reducing their concentration in the atmosphere to help protect the Earth's ozone layer. Under the Kigali Amendment, parties to the Montreal Protocol will phase down production and consumption of hydrofluorocarbons, commonly used in the refrigeration. Now, hydrofluorocarbons are introduced as non-ozone depleting alternatives to hydrofluorocarbons. 123 states and the European Unions have ratified the Kigali Amendment, and the US has not ratified the amendment yet. But in April 2021, it pleaded to do so. The Montreal Protocol began life as a mechanism to protect and heal the ozone layer. It has done its job well over the past 3 decades. The ozone layer is on the road to recovery. And that's what, we saw in some of the slide that how ozone layer is gradually getting, repaired, and the whole is getting repaired. The cooperations we have been under the Montreal Protocol is exactly what is needed now to take on climate change and equally existential threat to our societies. So that whole we are able to repair because we are knowing what is the gas that is causing this whole of the ozone layer. And similar way, the climate change, we have to identify what are the different types of provisions are there, at what layer, is it in the troposphere, stratosphere, ionosphere, mesosphere, where it is, so that we understand and act upon for the climate change mitigation. The Montreal Protocol is more than just an example of how multilateralism can and should work. It is an active tool to help meet our global vision for sustainable development. Under the Kigali Amendment to the Protocol, nations have committed to phase down hydrofluorocarbons, powerful greenhouse gases used as coolants. When fully implemented, the Kigali Amendment could prevent 0.4 degrees Celsius of global warming of the century. And that's a great achievement that if we are able to implement the Kigali amendment, that will essentially reduce 0.4 degrees Celsius. That is the prediction that has been made by through the process of a simulation, modeling simulation software. Furthermore, as we prepare for the Food System Summit this month, we are reminded that the Kigali Amendment can also help us to increase food security by reducing HFC, increasing energy efficiency, and creating more ozone and climate-friendly technologies. The Kigali Amendment can bring sustainable access to vital cooling services to millions of the people. Such devices would reduce food loss in developing countries where food often spoils before it can reach market. Getting produce from farmers to where it is needed would help reduce hunger. poverty, and the environmental impact of the agricultural sector. Another important benefit of expanding cooling is storage of medicines and vaccines, such as are needed to end the COVID-19 pandemic. The Montreal Protocol and the Kigali Amendment show us that by acting together, anything is possible. So let us now act to slow down climate change, feed the world hungry, and protect the planet that we all dependent upon. So I think this is the thing that I thought I must mention about it. And it is not only the Montreal, Montreal discussion that took place, or Montreal agreement that the Montreal Protocol that was decided, but most equally important is the Kigali Amendment. The Kigali Amendment needs to be, again highlighted, and it has a potential to reduce 0.4 degrees Celsius of the global warming. And it has also shown, once again I'm repeating, it has also shown that multilateralism, if people try to do it, we can do it. And like ozone hole, the way we have repaired it, it is again a collectivism. So if we collectively try it, nothing is impossible. So on this day of the ozone day, let us take a pledge among ourselves that whatever little bit we can influence to the policy interventions, whatever little bit we can influence to the academicians of the across the globe, to the policymakers in our country, that let us see that how best collectively we can recommend that how to really take care of the good ozone layer, and also how to remove the bad ozone layer. So thank you, Tonu. Thank you very much for taking this initiative. And this again, really, it also reminds us our responsibilities. It also reminds us that if we really want to survive, we have to survive through a collaborative approach, through the process of collectivism. So thank you very much.
Thank you, sir. Thank you for the insight, for such an enlightening session, informative session on ozone layer depletion and its effects on environment and health, and the various steps, as you already said, that we can take to prevent the event. Thank you so much, sir.
And we have already done it. And it is all multilateralism has worked out. And we have shown that it is possible. There's such a huge length that was visible as a whole. Now it is now on the path of recovery. This is again a process of multilateral collectivism.
Yes. Thank you, sir.
Thank you so much, sir, for your kind words and mentioning the Kigali protocol. And I think after
Kigali Amendment.
Yeah, and after the Montreal, this Kigali Amendment really made a difference. And now, but it has been recovering. But I think what my contention is that still, it should be completely filled. I think there are some more satellite programs are required through which it can be filled. Maybe we'll discuss later in this program further. Thank you, sir.
Now moving ahead, go green, go genius, stamp the carbon, stand tall and stitch the ozone layer. Save the layer which is up in the air. Without further ado, now I would like to invite our next speaker, Professor Umesh Kulshrestha. Dr. Chandra is currently working as a professor at School of Environmental Sciences, Jawaharlal Nehru University, New Delhi. Sir is also honorary director, Trans Research Cluster, JNU, and deputy director at South Asia Nitrogen Center. Dr. Kulshrestha earned his PhD from Dayalbagh Educational Institute, Agra. He has a double postdoc from National Physical Laboratory, New Delhi, and Department of Meteorology, Stockholm University, Sweden. Dr. Kulshrestha is a fellow of Indian Geophysical Union, IGU, and has received many awards and recognitions. Sir has various research publications to his credit. Welcome, sir. Over to you.
Welcome, Dr. Kulshreshtha.
Okay, so good afternoon, everybody. And I wish you a very happy Ozone Day in advance, though it is tomorrow, but for the sake of working day, we are celebrating it today. I thank Tanu Jindal for inviting me, and it's a, I think, second time or third time in Amity I'm speaking on Ozone Day. I think last time Dr. Bandhopadhyay was also there. So it's a good occasion that we are speaking about ozone and we are worrying about ozone. Much about ozone in stratosphere this day is celebrated, but tropospheric ozone is also not very uh, uh, basically less important not to cover it, because most of the activities they are affecting our tropospheric ozone. Most of our observations are also going on ambient air ozone, tropospheric ozone. So I will start from Dr. George left. I will share it, the screen. Are you able to see my screen? Are you able to see my screen?
Yes, sir. Yes, sir. Yes, sir.
Okay, good. So Dr. George in the last mentioned that during pandemic ozone was increasing. So I take from this point and just let you know that ozone was increasing not in pandemic but before pandemic, when EPCA started GRAP in 2018, somewhere October, November, GRAP was started, Graded Response Action Plan. And I was also member of EPCA, the EPCA, Environmental Pollution Control Authority, that was the body by Supreme Court. We used to look after this pollution in NCR, and GRAP task force were working under us, and they used to guide time to time in which sector, which direction industry should be closed, particular activity should be closed. So within few months, we saw the results. During our field visits, we were able to control plastic burning, illegal pyrolysis units which were using tires and making tire oils, making a lot of smoke, haze like situation in Delhi. In May 2019, almost 1 year before pandemic, many of you don't know, but those who are working in tropospheric ozone, they might have read our paper. There was news that in May 2019, ozone is increased at some locations in Delhi. You see here this graph. You can see 17, 18 and 18, 19. So May month in 19, you see orange bar that is showing that what happened to ozone. Normally ozone used to be somewhere 20, 30, that range. Then suddenly in 2019, it was 60, 70 days. And then I looked the data, CPCB, different stations, and I found that stations having a lot of burning activity, waste burning activity. Near those it was there, but it was not much around airport. But it was D2 was site where I found, and D2 is site where we have a lot of plastic industry waste disposal and plastic burning in Mondaka and that area you might have seen. In that area, we have seen piles of plastic, and the YouTube. So our committee did a good job with the consultation with the industry, and those piles were removed. And here I thank our committee chairman. Everybody knows he did good job. I used to go with him as a member of committee, and we had taken several meetings of different industries. Within few weeks of this exercise, things were very clean. And then this was the news in May month, the data, and then our background of atmospheric chemistry and different pollutants, like then we did some kind of analysis of data. And if you look at recent in same thing, if you compare in 19, it was the blue one, then the green one, and 20 again, when pandemic was there, ozone increased. This is D2 site, Narela Mondka area. So when we stopped burning, carbon was less during 18-19. Then further during pandemic, everything got stopped, no emission from any kind of source, whether fossil fuel or burning, plastic burning, any other combustion. So as a result, atmosphere was clean, visibility was good, solar radiation was good. So ozone formation was one. Before that, when plastic burning was there, a lot of carbon was there. So hazy conditions were not allowing sun rays to come, and ozone is all about photolysis reaction. If you look at this formation of ozone in stratosphere and troposphere, both processes are very different. In stratosphere, ozone is formed through Chapman cycle. It has 3 steps, and it is all about oxygen and combining and dissociating. So oxygen atom take part, and ozone at different wavelength it is formed, and it is dissociated at 220 to 320 nanometer. During the process, we have different kind of U rays and having different energy. So oxygen is also dissociated at 3 main wavelength, making mainly 3 types of atom, O1D, O3P, and O1S. So this is the process happens in stratosphere, where we have high energy coming from UV, and there only oxygen is taking part. Atomic O is coming out from oxygen, whereas in troposphere, the source of atomic oxygen is different, and that is up to now considered as so NO2. NO2 is having energy colliding with 380 and plus nanometer. It is split into nitric oxide and atomic oxygen, and that combined with oxygen make ozone. This is the source root here in troposphere, and we get NO2 from NO, nitric oxide coming out from mostly traffic and tailpipe that is converted to NO2. But in the atmosphere, when NO concentrations are less in equilibrium, that time we have peroxy radical, and that is the source of NO2. So this cycle happens. And how ozone is destructed, it has mainly two routes, one through HCl and other one is nitric oxide. Mostly last previous speaker, he was speaking about NO, and not many people they know that this is very new concept what we have given for this high ozone in India, especially in NCR region. That is due to stopping of PVC burning, old tire burning, and that is a major source of HCl. So up to now, we used to believe only the NOx and VOC chemistry. After this, once we have published, we have to further do measurements about chlorine and HCl as additional precursors of ozone other than VOC and NOx. Together with black carbon is also precursor, because when haze is there, haze is due to black carbon, the black carbon is due to burning, and so that affects solar radiation. So in a way, black carbon is also a precursor that should be studied. If you look at, as I mentioned, these further all details. Last point, if you see of the slide, the ozone level what we got increased in May 2019. After that also, they were at par with the rural area. Means rural area of that particular region, means geographical location. If you see, we are getting that many sun rays. So it's a natural background. Means before that, during burning period, due to plastic burning, PVC burning, tire burning, this was suppressed. Ozone levels were suppressed. And now, when weather is clean, visibility, the sky is blue, these are at natural level. So we should not worry about that. It doesn't mean that we should not worry about environment. What I mean that the normal level, even increased levels are within the limit permitted by national ambient air quality standards. So increase is still not much. It's within the limits. And already this we know that healing has continued, and this healing is clearly seen in these figures. But one thing which I want to add in this one, that in March 20, everything was reduced, so ozone was increasing, and there was clear-cut indication that the pandemic has helped in the filling of this ozone. But at the same time, that organization controlling Montreal Protocol, and that they also added, because just so that all the efforts should not go waste, they told it's due to control of CFCs, not purely control of pandemic. So we should keep in mind that this kind of differentiation also should be validated by different kind of experiments, because it's a global concern. So any kind of doubt and kind of statement should be taken very seriously. So if you look at this, even the CO2 levels and Mauna Loa, they got increased, and the whole thing, once upon, I was teaching before this pandemic, I was teaching our students air pollution, and there was a discussion about how to know whether this is happening due to anthropogenic or not. In that class, I mentioned, if something happens which is not practical, if everything get closed, and then we will come to know what are the levels, and this happened after few months or so. So this way, this is confirming the IPCC findings that 90% certainty is there that human activities are responsible for global warming is due to carbon dioxide, but all these are connected because the common sources are fossil fuels, burning, all human activities. So from that angle, this is sure that pandemic was natural experiment, this sort of control experiment for all of us, those who are working for atmosphere. And that has given idea that whatever human activities we do, they are really spoiling the air, and the background levels were identified during pandemic. Taking that, for example, even ozone was identified as background level, and that levels what we have, these are background level, these are not increased level, we should not consider at all. Another proof for this this happened due to plastic burning control. These are photographs, and you see these photographs are taken during 19 August, means when GRAP was implemented. Burning was very much controlled. The photographs taken from IIT to expressway, Yamuna expressway near that building, clear. So the visibility increased. Even this from IIT to Badarpur thermal plants, it clearly indicated that during that period also visibility was better, and because of that only in May month we saw ozone spikes. If left side, if you see this PM concentration decrease during GRAP. So wherever flags are there, these they indicate. After that, immediately we have a drop. ITO and D2 side, these are this is our research. One of my students he did. So these are some kind of proof that we have to work on this, because this is new kind of suggestion and research. It's not traditional one where you have lot of material. This is very beginning comments and kind of hypothesis built based on some available literature and our experiment, and also indirect experiment. I would like to share here our previous research in 1996 around. We did around 25 years back. Some of you may be remembering that plastic market is there, Jwala Hedi, and there was a fire, huge fire, and lot of material got burnt, and we used to see thick carbon in the sky. And that time we collected some samples of dust fall. In the dust fall samples we collected, and we found chloride the highest, anion, followed by sulfate nitrate. Normally we were having continuous studies, and normally we used to have sulfate nitrate higher than chloride. So the water soluble chloride was high, and that was the reason it was coming from plastic. So the connecting this previous work to my this EPCA experience, we confirm that plastic burning was the major source of carbon and major source of HCl that was quenching that time ozone levels, and when this was clear, and then no HCl was there, no smoke was there, and this as I have demonstrated here. You can see this chart, and there are two conditions: one, plastic waste burning, and no plastic waste. Right, right. So if you have plastic waste burning, then you have emissions of chlorine, carbon. Then one side it creates haze, then it creates lower solar radiation, and then low ozone formation, and finally net low ozone. When you have a lot of carbon and chloride, then quenching takes place, ozone is decreased, and net ozone is lower. But when you have no plastic burning, clean like pandemic and May 29th the scenario I mentioned, then there is no chlorine species, then no quenching of ozone, no age, we have higher visibility, higher solar radiation, and we see higher, and this is something we had after EPCA, and the left one we had before EPCA. And the chlorine, as it it's a chain molecule, chlorine radical as a chain molecule. This was recognized, and the Nobel Prize was given to Roland and Molina in 1995, and Paul Goodgen got for NO as the attacking molecule that is normally associated with NOx chemistry. And I'm glad that I did postdoc with the same department where Paul Goodgen was also there once upon a time. So this is something new story of ozone high in NCR region, and we have to do several efforts for ozone and its precursors. We need to regularly monitor ozone, its precursors BC, VOC, NO, HCl, Cl2, chloride. Then we have to see how much quenching is there to HCl, how much chlorine gas. Then if at all it's there, then we have to quantify the quenching of NO versus quenching of HCl. And then we have to see the impact of black carbon haze on production of ozone. Though there are several studies, but in NCR region, we have to have these type of studies. There was saying that because the pandemic has a lot of use of sanitizer, so it has increased due to that. So that also should be studied measurement wise or modeling wise. Then role and interference of atmospheric dust, because ozone is having a nature of greenhouse gas, and we have dust a lot of in India. So there are reports it interferes, and kind of radiative forcing also it has. So those studies also should be done. Accordingly, we need to have a policy to support more research. So this is something required, and this is in favor of a clean air, blue sky, those aspects, climate change. Because when we talk about pollution, we have to think that in NCR we have pollution, mainly particulate pollution, PM 2.5, PM 10, and out of that, the important one is carbon. So if we stop carbon, we stop basically more pollution. We control pollution, and preventing carbon sources, we prevent pollution. So that with that suggestion that we control carbon, we control, I think, most of the pollution in NCR. Thank you very much. Hello.
Thank you.
Thank you, sir.
Thank you, Dr. Kulshesh. It's a
Thank you,
very
sir, for
sharing your own research work plus also general about the ozone formation. So I think your work has a lot of scope. We need to really analyze at each and every station where ozone levels are rising, because it is directly having health impacts. So there is a lot of scope. We can really formulate a project on that and we can submit for the further analysis for the precursors as well as ozone. Thank you so much.
thank you, sir. Now, moving ahead, sunshine is the panacea to all diseases, but without ultraviolet rays.
Yes, Smriti,
Yes, ma'am.
Dr. KB George is also ready with some of his slides. So if he can share his slides with.
So next, ma'am, next speaker is Dr. Anikender. No? You are not audible, ma'am. Yes.
Dr. George, would you like to wait for some time? Then maybe we can take up. Dr. George?
Sure, madam, sure. Let everything be
Yes, sir.
over, and if time permits, then only I'll show some of
Okay.
few more
Okay.
slides. That's all.
Great.
Yeah.
Great. Yeah, great. Yeah. Please, Smriti, call the next speaker, please.
Yes, yes. Reduce depletion of ozone, otherwise you will be in the red zone. So without further ado, Dr. Aniken Kumar with us. Dr. Kumar is a renowned scientist at India Meteorological Department, New Delhi, and visiting scholar at University of California, Davis, USA. Sir has obtained his master in mathematics from IIT Roorkee and PhD in atmospheric sciences from IIT Delhi. Before joining IMD, Sir worked as a postdoc researcher at University of California, Davis. His primary area of interest is mathematical modeling of air pollutants, chemical transport modeling, climate change, and source apportionment of air pollutants. Sir has published more than 40 research papers in various international journals and conferences. Welcome, sir. Over to you.
Thank you very much, ma'am. And good afternoon to all. So I'm just going to share my slide. I hope the slide is visible. Yeah, ma'am. Slide is visible.
Yes, yes.
Okay.
Yes, sir.
Oh, it is moving.
Yes, sir.
Okay. Thank you very much. So thank you very much to all of you. And so today I'm just going to, because already 3 or 4 speakers have already talked about the ozone. So it will be just like a summary for all these things. So this is an introduction of the ozone and ozone hole in the changing climate. So if we will talk about the ozone, so first time the ozone was suggested by the German chemist Christian in the 1814, and he firstly suggested the existence of the ozone. And following the electrical discharge in the air, he identified a peculiar odor that he named after the Greek word ozone, and the meaning of the ozone in the Greek, it is the smell. After that, in the early 20th century, Charles Fabry and the GMB Dobson independently conducted the experiments that yielded the quantitative measurement showing the existence of the ozone layer in the upper atmosphere. And later on, the fundamental chemical reactions responsible for the ozone layer were first proposed by the Champion in the 1930s. So it is just an introduction that when the ozone term was introduced. So for ozone, we already know, and we have already seen in the previous presentations, that without ozone, we cannot live, and with higher concentration ozone, we can also not live. So for the troposphere, if it is going to be high, it will be the bad ozone. For the upper atmosphere, in the stratosphere, it is good for us. So before starting to the ozone, I just want to show the thickness of the atmosphere, because ozone is very much needed or it will very much related for this thickness of the atmosphere. So in the right hand side, if you will see, this is the temperature profile. So the temperature will decreasing in the troposphere. After that, it is increasing in the stratosphere. So in the increasing of the stratosphere, the ozone is one of the main parameter or variables. So here we can say that there is no defined top for the atmosphere, and if you will consider it's a 10,000 kilometer, after that the atmosphere will blend into the space. And our 99% of the atmosphere in the Earth is below 32 kilometer, and all the weather activities are lie in the 11 kilometers. So we can see the troposphere. All the weather activity occur in the lowest atmosphere. We can say to the troposphere. This is just a variation of the temperature, and here for long it was thought that the temperature decreases with the altitude. But when we have the radio sonde where we can measure the temperature with a different height, and it was started in the 1900s, it was observed that the temperature is increasing in the layer between 10 to 18 kilometers. And this discovery of the reversing the temperature trends led to the division of the atmosphere. So after that, we have the troposphere, stratosphere, mesosphere, as well as the thermosphere. So in the troposphere, troposphere contains around 75% of the atmospheric mass, and all the weather changes, including the cloud activity, occur also in this layer. And the height is in between 8 kilometers to 18 kilometers, but it will depend whether we are at the poles or whether we are on the equator. And the temperature decreases with the height in the troposphere. After that, the stratosphere. This is the second layer, which is above troposphere and up to the 50 kilometers. And temperature is going to increase in this layer in the stratosphere due to the UV radiation is absorbed by the ozone. So here, ozone becomes very much important. So due to that, our temperature is increasing in this layer. So what is ozone? So ozone is a trioxygen, is an allotrope of the oxygen that is much less stable than the dynamic allotrope of the, or we can say the oxygen, O2. So ozone is a colorless, odorless gas at the ambient concentration. So ozone is present in the low concentration throughout the Earth atmosphere. In the total, ozone makes up to only 0.6 parts per million of the atmosphere. So if we can consider that only in 1 million parts, ozone is only 0.6 parts. And the total mass of ozone in the atmosphere is about 3 billion metric tons. So this is just about the ozone, that ozone is a gas made of the 3 oxygen atoms, which occurs naturally in a small trace amount in the upper atmosphere, in the stratosphere we can say. And the ozone protects the life on the Earth from the sun ultraviolet UV radiation. In the lower atmosphere, the troposphere, near to the Earth's surface, ozone is created by the chemical reactions between air pollutants from the backload exhaust, gasoline vapors, or the other emissions. At the ground level, high concentration of ozone are toxic to the people and the plants. So we must take care for the higher concentration of the ozone at the surface level. So this is just a snapshot that how is the variation of the ozone. So if we can see that in the stratosphere, ozone concentration is high, or we can say in between 30 to 35 kilometers, we have the maximum concentration of the ozone. In the lower atmosphere, if we will see that in the near to the surface, it also increases. So, and it is due to our anthropogenic activities. So the concentration of ozone varies with the altitude, and it peaks with an average 8 molecules of the ozone per millions in the atmosphere, and between the altitude of 30 to 35 kilometers. Later on, before moving to the ozone, this is just in the electromagnetic spectrum, because it is very much important, because ozone and the ultraviolet radiation has a very good relationship. So if we can say the wavelength, ultraviolet radiation has the 7% of the radiation intensity. Visible real light has the 44% maximum. After that, we have the near infrared or far infrared, or some other this wavelengths, whether it is a microwave or the radio waves. So if we will talk about the ultraviolet radiation, which have only the 7%, but we can divide, it is divided into the ultraviolet radiation of A, B, and C. So ultraviolet radiation A, it is 315 to 400 nanometer. B, it is 280 to 315, and C, it is the 100 to 280 nanometer bands. So ultraviolet C, it is nearly all the ultraviolet C is absorbed in the upper atmosphere. B, around 90% of ultraviolet B is absorbed by the atmosphere, mostly by the this ozone. And ultraviolet A, it is not strongly absorbed by the atmosphere. So now, firstly, we will understand the production of the stratosphere. So for stratosphere, ozone is naturally formed in the chemical reaction involving the ultraviolet sunlight as well as the oxygen molecules. So in the right hand side, if we see in the step 1, we have the 2 molecules of oxygen in the ultraviolet sunlight. It will break into the single atom of the oxygen. And after that, this single atom of oxygen, and it will combine with the 2 atoms of the oxygen, and it will make the ozone. So this is the formation of the ozone in the stratosphere. After that, we can say the ozone is also destroyed naturally in the stratosphere, and it will be dissociated by the ultraviolet radiation. So we have created, or it was created, ozone, and in the presence of the UV photon, it will break again into the oxygen, 2 molecules of the oxygen and the single atom. And after that, again, this single atom will combine with the ozone and it will form the 2 molecules of the O2. So the formation of the ozone and the destruction are normally in a steady state in the stratosphere, such that the rate of its formation is equal to the rate of its removal. So means we can say that it is not increasing or decreasing in the stratosphere. This is just a natural ozone destruction, the same which we have seen in the previous slide. So this is, we can say, the champion process of the ozone destruction. So ozone absorbs a range of the ultraviolet radiation. After that, it is splitting into the molecules into the 1 free oxygen atom and 1 molecule of ordinary oxygen. And this free oxygen atom then collide with another ozone molecule, and then it will form 2 molecules of the oxygen. So till now we just understand the stratospheric ozone. Now we will talk about the tropospheric ozone. So this is the ground level ozone formation. So it will happen with the NOx and the VOCs in the presence of the sunlight. So it will form the ozone. So tropospheric or the ground level ozone is not emitted directly into the air. So that's why the ozone is a secondary pollutant, but it is created by the chemical reactions between the oxide of the nitrogen, NOx, as well as the VOCs. And the tropospheric ozone has an atmospheric lifetime range of a few hours to few weeks in the polluted urban regions. And sources, it can be from the industries, it can be the electric utilities, motor vehicle exhaust, gasoline vapors, as well as the chemical solvents. This is just an showing again the tropospheric ozone formation. It is same that ozone will form with the help of the NOx as well as the VOCs in the presence of the sunlight. So this tropospheric ozone, so in the stratosphere, provides a shield to protect the life on Earth, and directly contact with the ozone is harmful to both the plants as well as the animals, including the humans. But ground level ozone is bad ozone, forms when the nitrogen oxide gas from the vehicular or industrial emissions react with the VOCs. So it can form there. This is just a dynamic variation of the surface ozone at urban or as well as the rural locations. So if we will consider the agricultural college as the rural areas, and the patient as the urban areas. So if you can see in the night time, the ozone concentration is lower in comparison to the daytime. So it is due to the presence of the sunlight. But if you can see even in the night time, the concentration of ozone is higher in these urban areas in comparison to the rural area. And in the daytime, also rate of ozone is increasing, but the magnitude is lower than the urban areas. So this snapshot is for the January 2007. In the right hand side, it is just the diagonal variation of the ozone or surface ozone with the temperature as well as the relative humidity. So we can see that when temperature is increasing, the ozone is increasing, but when the relative humidity is decreasing, then this ozone is increasing. This is actually very much important, the NOx to the VOCs ratio. So everyone, most of the paper has published after the COVID that during the COVID, most of the pollutants was decreased, especially the particulate matter. But most of the areas all over the world, the ozone concentration was increased. So ozone is not only depend NOx, because most of our emissions of the NOx was decreased during the COVID lockdowns period, but it also depends on the VOC. So in the left hand side, this is the NOx versus the VOC isotope. So here we have the NOx limited area as well as the VOC limited area. So in the troposphere, this ozone is produced in a complex cycle of the photochemical reactions involving nitrogen oxide NOx as well as the VOCs. So what is the NOx sensitive area? So it will determine if the ozone levels will be decreased by decreasing the NOx emissions. And the VOC sensitive areas will be those areas where the ozone levels are decreasing by decreasing the VOC emissions. And there will also be the transit zones. So it will show when the ozone level will be decreased by decreasing the NOx as well as the VOC emissions. So after that, what is the health effect of ozone? So ground level ozone is a pollutant that is harmful to living organism. Level of surface ozone exceed 80 parts per billion for the 8 hours or longer are considered to be harmful for the most living things. So in the right hand side, if we can see, this is the healthy line, but when it was inflamed by the this ozone, then it has been changed. So ozone can inflame or damage the cell that line your lungs. Ozone may aggravate the chronic lung diseases. Ozone may cause the premature lung diseases. In addition to this, the ozone can cause the coughing as well as the throat or the especially throat, and it can make more difficult to breathe deeply. It can inflame or damage the airways. It can make the lungs more susceptible to the infection. And even for the long-term exposure of the ozone, air pollution is linked to the 1 million premature deaths per year due to these respiratory diseases. This is the effect of the ozone on the ecosystem as well as the agriculture. So ozone can reduce the photosynthesis, which is the process that plant use to convert sunlight to the energy to live and the grow. It can make the slow the plant growth. It can changes the specific assortment of the plant present in the forest. It can change the habitat quality. It can change the water as well as the nutrient cycle. And on an average, it was estimated that global crop production is around 79 to 121 million tons, and which we consider the cost around 11 to 18 billion annually due to these ozone. After that, the ozone is also the effect on our climate. So ozone is a major product of the air pollution, and globally, the dependence is unknown. So ozone at the Earth's surface plays a key role in the chemical cycle to many other trace gases in the troposphere. So if you will see in the right hand side, we have the radiative force of the for the year 2005 in comparison to the pre-industrialization time, which we consider as the 1750. So if we can see that carbon dioxide is a greenhouse gas, and it is this radiative forcing is around more than 1.6 watts per meter square. After that, second pollutant is methane, which is also more than 0.4. But at the third place, it is the tropospheric ozone. So it is also very much important, or even it is also increasing the temperature of our Earth, and it is around more than 0.35 watts per meter square. So ozone has an effect on the health. It has the effect on our ecosystem as well as the agriculture. And the third one, ozone has also effect on the climate. So these are just some significant values. So on an average concentration of the ozone can be between 0 to 100 parts per billion. It will depend on the time of the year as well as the geographical location. In the extreme condition, it can reach more than 200 parts per billion. And levels of the surface ozone, if it is going to exceed the 80 parts per billion for the 8 hours or longer, are considered harmful for the most living things. So now, before moving to the ozone hole, firstly, I just want to introduce the Dobson unit. So Dobson unit of the ozone correspond to the layer of 1 millimeter thickness at standard temperature, 0 degrees centigrade, and pressure. So 1 Dobson unit would contains 2.69 plus 10 to the power 16 ozone molecules for every square centimeter. So over the Earth's surface, the ozone layer average thickness is around 300 Dobson unit. So we can consider the layer is 3 millimeter thickness. So on an average, if we will make our all the atmosphere in a vertical column and we can suppress it, then we can get around 8 kilometer thickness of our atmosphere. In that atmosphere, we have the layer of the ozone is only 3 millimeter. So this ozone concentration on an average is very less, but it is very much important, and as well as it is very harmful if its concentration is increasing at the surface level. And we can say that the healthy ozone layer is in between 240 to 500 Dobson units. After that, this is the ozone hole. So ozone hole technically is not a hole. Here no ozone is present, but it is actually a region of the depleted ozone in the stratosphere over the Antarctic that happens at the beginning of the southern hemisphere spring, August to October. So average concentration of ozone in the atmosphere is around 300 Dobson unit. But if any area where the concentration to cross below the 220 Dobson unit, it is considered as the ozone hole. So ozone is created when the kind of oxygen this O2 is split apart by the sunlight into the single oxygen atom, and this single oxygen atom can be rejoined to make O2, and they can join with the O2 molecules to make the ozone. So however, ozone is destroyed when it reacts with the molecules containing nitrogen, hydrogen, chlorine, or bromine. And some of the molecules that destroy ozone occur naturally, but people have created others. So this is the historical record. We know that the Coleman ozone values of less than 220 Dobson unit were not observed prior to the 1979. From an aircraft mission over Antarctica, we know that the total Coleman ozone level of the less than 240 Dobson unit is a result of the catalyst ozone loss from the chlorine and the bromine compound. For this reason, we use 220 Dobson unit as the boundary of the region representing the ozone loss. This is just a snapshot from the OMI ozone concentration for the October 4, 2004. This is just showing the history of the ozone hole. So in the early 1912, Antarctic explorers recorded the observation of unusual being of the clouds in the polar stratosphere, although they could not have known at the time how significant those clouds would become. And in the 1956, the British Antarctic Survey set up the Harney observation on Antarctica in the preparation for the International Geographical Year, which was happened in the 1997. In that year, the ozone measurement using the Dobson spectrophotometer began. So if you can see from the 1957 or 58, we can see that this is the total ozone concentration. And we can see that it was decreasing. We can see in the 1985 when we discovered the ozone hole. So this is with the different instruments as well as the satellite measurements. So here we can see the Harney, which has the Dobson spectrophotometer, TOMS, OMI. These are the satellite measurements. So we can see that after 85 or 80s, this total column ozone was decreased significantly, but now there is slightly improved. This is the history of the ozone. These measurements gave the first clue that there were trouble in the ozone layer. So in 1985, a group of the scientists formed and the tracking of this journal Nature, the first paper on observation of the springtime losses of the ozone for the Antarctica. Again, in the 1986, NASA scientists also used the satellite data, and they also found the same. results. In the between 1986 to 87, several papers suggested the possible mechanism for the ozone hole, including the chemical dynamic or the solar cycle influences. This is just a snapshot that how it is changing between the September and October. This is the vertical variation of the ozone. So we can see on the September 1st, we can take the average from 1951 to 2014. The ozone concentration at the stratosphere is around 228 with an uncertainty of the 25%. But if after that it is decreasing, and on the October 5th, you can see that ozone concentration, the vertical variation is too low. This is just a snapshot for the seasonality of the Antarctica ozone hole. So we can also see here that this is the Dobson total column of ozone. So it is decreasing. So after August, it is decreasing sharply. And it is after that, the November or October, December, it is increasing. So this is the main area for the ozone hole period. Again, we can see the temperature times region. In the lower part, we can see this is the snapshot for the ozone, the vertical distribution of ozone. On the 28th of July, the ozone is higher concentration, but we can see in the September 29, it was very much less in comparison to the July as well as the December. This is the Antarctica ozone hole trend. So we can see that after the discovery of the 85, this is the trend. So we can see that there was slightly improvement. So our gross, we can say it's ozone hole area was 26.6 million square kilometer, and in the last year it was 23.2 million square kilometer. In the left hand side, this is the ozone hole area for the 2023. So it was just till September 1st. So we and after that we don't have the data from last 10 or 12 days. So but they will update it. So we can see in the July 1st, the ozone hole area was only 3 million of the square kilometer, and but in the September 1st, it reached the 20 million of the square kilometer. This was the story for the ozone hole. So these scientists have the Dobson spectrophotometer, and the appearances of the ozone hole on the Earth layer. Antarctica was detected in the 1976, and they were so unexpected that the scientists did not pay attention to what their instruments were telling them. So, but after that, other researchers as well as other studies also saw the similar type of the study. So, after that, the Antarctica ozone hole was discovered in the 1985 by the British scientists. So what are those key ingredients which are making the ozone hole? Chlorine, which is supplied from the man-made chlorofluorocarbon, cold temperature, season, clouds, as well as the UV radiations. So this is the chemist Thomas Whitcay Jr., who was the industrial chemist who developed the non-flammable, non-toxic compound chlorofluorocarbon to replace the hazardous compound that were using in the refrigerator. After that, these chemicals have extensively used after the 1960s. So if in the lower side, we can see that what was the values for these polluted chlorofluorocarbon, it was only 12, it was only 100 parts per trillion in the 1960s. After that, it reached, it became double in the within the 15 years in the 1975. Again, it was double, and it reached to 400 parts per trillion by again in the next 12 years. So by 1990s, they detected more than 750 parts per trillion of the chlorofluorocarbon 11 as well as 12, the most destructive and the persistent chlorofluorocarbon. So again, these three scientists, they found nitrogen, chlorine, and the bromine ozone chemistry in the 1962. Hardly makes a point about the chlorine and the bromine catalyst reaction that could destroy the ozone. In the 1970s, while examining the potential impact of the supersonic transport on the stratosphere, atmospheric chemist Paul Wilson identified an ozone-destroying catalyst cycle in the oxide of nitrogen. And in 1974, Manuel and the Shepard rover blames this cycle to the chlorine in the chlorofluorocarbon. So on that basis, they got the Nobel Prize of 1995 for their work on the stratospheric ozone depletion. This is just a snapshot for the UV radiation of chlorofluorocarbon, which we can understand here a little bit more. This is, we can call the unnatural ozone destruction. So chlorofluorocarbon are the non-toxic, non-flammable chemical containing atoms of the carbon, chlorine, and the chlorine. They are used in the manufacture of the aerosol spray, blowing agent for the foams, and the packing materials as the solvent, and in the refrigerators. So we can see here that in the we will get the this chlorofluorocarbons from the factories and the foam spray. It will reach there, and in the sunlight, it will break down the chlorofluorocarbon into the stratosphere, and after that, it will break down the products for destroy the ozone. And in the fourth one, the scientists sent up the balloons to see where all the ozone will go. So this is the Antarctica ozone hole during the southern hemisphere. Winter, the lack of the sunlight over Antarctica causes the temperature to drop. At very cold temperature, you can say minus 80 degrees centigrade, certain chemical reaction involved with chlorofluorocarbon causes an increase in the concentration of the chlorine gas. And when the sunlight returns, it splits the chlorine gas into the chlorine radicals. And these chlorine radicals then rapidly accelerate the ozone depletion. So as a result, we can see the sharp decline of the ozone from September to the November. So what are the mitigation strategies this world has applied or they have adopted? So through the 1970s and 80s, the international community became increasingly concerned over these ozone depletion substances that are harmful for the ozone layer. So in the 1985, there was the Vienna Convention for the Protection of the Ozone Layer. You can say it's a formalized international cooperation for this issue. After this issue, or this cooperation resulted into the signing of the Montreal Protocol for the substances that deplete the ozone layer in the 1987. After the Montreal Protocol was signed, new data showed worse than the expected damage to the ozone layer. And in the 1982, the parties to the protocol decided to alter the terms of the 1987 agreement to end production of halogens by 1994 and the chlorofluorocarbon by 1996 in developed countries. Because of measures taken under the Montreal Protocol, emissions of these ozone depletion substances are falling, and the ozone layer is expected to be fully healed near the middle of the 21st century. Again, in the Vienna Convention, adopted in the 1985, the Vienna Convention for the protection of the ozone layer is the precursor of the Montreal Protocol. And this Vienna Convention is often called a framework for the convention because it serves as a framework for effort to protect the global ozone layers. Again, the Montreal Protocol, it was originally signed in the 1987, and it was the first step in the international effort to protect the stratospheric ozone. After that, there was some amendment. We can say the London Amendment in the 1990s. They have changed the ozone depletion emission schedule by requiring the complete phase out the chlorofluorocarbon, halogens, and this carbon tetrachloride by 2000 in developed countries and by 2010 in developing countries. After that, there was the Copenhagen Amendment, which was happened in the 1992. It was significantly accelerated the phase out of these ozone depletion substances and incorporated hydrochlorofluorocarbons, HFCs, phase out for developed countries beginning in 2004. Under this agreement, CFCs, halogens, carbon tetrachloride, and the methyl chloroform were targeted for complete phase out in 1996 in developed countries. There was other amendment in the Montreal Amendment, which was happened in the 1997. It was included to phase out the FFCs in the developing countries, as well as the phase out of the methyl bromide in the developed and developing countries in 2005 and 2015, respectively. And after that, this was the Beijing Amendment in the 1999, which was included the heightened control on the production or the trade of the HFCs. And this chloromethane was also added to the list of the controlled substances with phase out targeted in 2004. And after that, it was the Kilagir Amendment in 2016, extended control to phase out the production and the consumption of these HFCs, because these substances were adopted by industries in moving away from the ozone depleting substances, and they are potent greenhouse gases damaging to the Earth's climate. This is just a model prediction. So this, because if we did not, it was without assuming that we did not control these CFCs, or we did not ban these CFCs emissions. So here you can see in the 1975, we have this total column ozone was more than in the range of 300 to 400. In the 1994, it was in between 250 to 350 around. After that, it was also in 2009, it was also from 200 to 300 range. In 2020, it was also in 180 to 200 range. If we can see the motor production in the year 2014, it was also in the range of around 200 option. But if you will see in the 2060, if we did not ban these chlorofluorocarbons, the ozone concentration will be below. Means around 150 Dobson unit. These were some consequences of the ozone layer depletion. It can increase ultraviolet radiation. It can have the biological effect. It can increase the tropospheric ozone, which is also a greenhouse gas, which can also increase the production of vitamin D. It can affect on the animals as well as the crops. After that, this is how we can measure or how we are measuring the ozone, taking the measurement in India. So this is the first ozone measurement was taken in the 1928-29 at the Kodaikanal as a part of the Dobson Worldwide campaign for the total column ozone measurement. And IMD acquired the first Dobson spectrophotometer in the 1940s. And IMD has also a network of the surface ozone network. And we have also developed an Indian ozone sonde, which was developed, or it was using IMD from the 1964. So in the right hand side, we can see that we have around number of the station from the surface ozone, where we are using the ECC method or chemical methods to measure the surface ozone. We have the two stations to use the total column ozone at the Delhi as well as Varanasi. And we are also using the vertical ozone profiles basically at the So ozone can, this is some techniques. So there are the two principles. One is the local measurement, another one is the remote sensing measurement. So in the local, we can say that we can measure the ozone to the ultraviolet absorption photometry. So this is just a snapshot for the ultraviolet absorption ozone analyzer. So here we are using the absorption wavelength of 254 nanometers. And the concentration of ozone is directly related to this absorbance. After that, IMD is using the electrochemical conductivity cell method, ECC method, to measure the surface ozone. So here we are using this potassium iodine, the cathode solution as well as the anode solution, and we can measure the ozone from this method. After that, we can measure the total column ozone through the Dobson spectrophotometer as well as the Wilbur spectrophotometer. In the left hand side, this is the Dobson spectrophotometer. In the right hand side, this is the Wilbur spectrophotometer. So this is the Dobson spectrophotometer. It is used different slit. So they use the UV1 and UV2, which enter through the slits S2 and S3. So this we can measure, or this detail we can learn in this Dobson spectrophotometer network. This is just a list for the Dawson spectrophotometer of what is the status in India. So right now, Dawson spectrophotometer, we have two Dawson spectrophotometer, a standard one at New Delhi and another one at also at Delhi. Varanasi, it works till the 2019, but now there is some maintenance or calibration is required for that spectrophotometer for Kodaikanal or Srinagar are not working right now. Bluebird spectrophotometer, we have the 5 Bluebird spectrophotometer. Two means these are not operational, but 2 Bluebird spectrophotometers are calibrated or repaired. So now most probably within next 1 or 2 months, this Bluebird spectrophotometer will work or it will be operational. This is some snapshot for the observation at the Antarctica. So in the right hand side, this is the from the ECC method we use the ozone concentration. In the left hand side, you can see that they are using they are just taking the ozone zone data. This is we are also taking the measurement in the New Delhi, and they are preparing the flight for the ozone zone. This is in the top one, it is for the Bharti station, and the lower one, it is the Maitri station. This is also some we are taking the observation at the Antarctica. They are just trying for the ozone zone. This is some data, or we can say some results. So this is the vertical profile. We can see in the 13th of October 2017, the ozone was around 15 or 16 maximum here. So we can see its status here. And after that, in the 20th of October, it was increased. We can also see in the satellite measurement at the Bharti, it was around 184 Dobson unit, and which was increased on the 20th of October. It was 408 Dobson units. These are some satellite measurements. So right now, INSAT 3D, which was launched in the 2003, and the INSAT 3DR, which was launched in the August 2016 from the ISRO. So we can also measure this ozone concentration or total column ozone. In the right hand side, these are some correlation or the evolution against the AIRS satellite. So what we can do, so we can become the ozone friendly consumer, we can become the ozone friendly homeowner, we can become the ozone friendly farming, we can become the ozone friendly citizen. And how you can protect yourself to avoid the excessive sun exposure. You can take the extra precaution because the unprotected skin and eyes will be damaged and can burn quickly. So we can wear the sunglasses on the bright days. And when outdoor in the sun, use the sunscreen or the umbrella, or wear a white print hat and protective clothing. So this is just a snapshot that how we can measure it in the middle of day. If our shadow is minimum, then it means that the sun ultraviolet rays are strongest, and if your shadow is shorter, then so take care of your appliances to minimize the ozone layer impact. So you can use the refrigerator, air conditioner, and the other equipment responsible to assist in protecting the ozone layer and the climate. So thank you very much. So
thank you, sir, for such an enlightening session on ozone layer depletion, its effects on environment and health, and the various steps that we can take to prevent the impact. Thank you so much, sir.
Thank you, Dr. Nikhil, for such wonderful. I think it has covered everything right from Indian perspective, Indian, work in this area, and you have really, explained everything in detail, right from ozone units, protocols, one by one, and then what is the future, perspective and how we envision at 2060 that it will be filled, there will be no ozone. I'm really grateful to you for sparing your valuable time. Thank you.
thank you very much.
Moving ahead, now I would like to invite Dr. W. Silva Murthy, sir, President, Amity Science, Technology and Innovation Foundation and Chancellor, Amity University, Chhattisgarh, for sharing your views with us on this very important event, Ozone Day. Welcome, sir. Over to you.
Thank you. Thank you very much. First of all, let me compliment Dr. Tanu Jindal. She is a great prime mover for this program. Religiously, she organizes every year all those connected with climate change, global warming, ozone layer depletion, this World Ozone Day, all this she meticulously organized, bring the right experts. I was just listening to Dr. Anikender Kumar for a wealthy treasure of knowledge, repository of information, which you gave, Dr. Kumar. You know, this is a wonderful lecture I listened. So my compliments to you and the wonderful work that you and the IMD is doing, and my great efforts and best wishes for you to succeed in the years to come. So we will also collaborate with you. Tanu Jindal will be already planning collaborations, and she might be already interacting with you. And so thanks for your wonderful lecture. And also all the participants. See, we have a big responsibility. Our ancestors, we have all caused damage, harm to the environment, the Mother Earth, the atmosphere. So it is our responsibility to see that how do we allow them to heal? Because nature has got its own ability to heal, whether it is ozone depletion, ozone hole, or the other. Nature has such a great resilience. All that you need to provide is the time for that to heal and the enabling the ecosystem for the environment to heal itself. So that is why this Ozone Day is being celebrated. And Tanu Jindal regularly organizes every year, bringing experts and also implementing the recommendation. So that is also the quality of Dr. Tanu Jindal. So thank you, Tanu, for this wonderful effort that you are doing here.
Thank you.
India is committed for sustainable development, because this is not only our Prime Minister, Honorable Prime Minister, but also the whole people of India are committed to have inclusive growth and sustainable development. So the whole policies, practices in our system are aimed towards that goal of sustainable development and inclusive growth. Even in the recent G20 summit, which concluded very successfully under the able leadership of our Prime Minister Shri Narendra Modi ji, that this was the focus. The climate action group was one of the major focus in the deliberation, and the climate change. How do we mitigate climate change? What should be the action plan? How do we advance the targets which we have set for the nations, G20 nations? So this was a great focus in the G20 summit also. And India is committed to UN SDGs, Sustainable Development Goals, and all the 17 goals, which we have prioritized the first 12 goals, and then we will also implement all the 17. And we want to become carbon neutral, not only by 2070. The Prime Minister and the country is working towards how do we advance it even earlier. So all this is a serious effort from Indian government, Indian scientists, Indian people. So I want to tell the world community that India is committed towards Montreal Protocol compliance and its implementation. We have already taken many steps towards. One is electric vehicles, for example. We want all transportation and mobility to be on electric platforms. So like this, there are many, many initiatives, sustainable agriculture. And also we are talking about sustainable energy, green energy, clean energy. So all these efforts are towards that. When I was in DRDO, we started the halon banking. You know, I was very happy to see Dr. Anikender talking about this CFCs causing this problem. So DRDO worked in the defense. There's a lot of firefighting systems that are available in tanks, aircrafts, and other platforms. So we have all replaced the halon, which was used there, by the alternatives, which is not ozone hole producing substances. So we did the halon banking in DRDO. Then we also looked at, through our research and development, CFC alternatives. So these were the efforts when I was in DRDO, I was associated. Now in Amity, founder president, Dr. Ashok K. Chauhan, the founder of this whole Amity universe, has established and taken many initiatives in this direction. First is establishing the relevant institutions, Amity Institute of Natural Resources and Sustainable Development. Amity Institute of Environmental Sciences, Amity Institute of Environmental Toxicity, Safety and Management, Amity Center for Global Warming and Climate Change. So all these are institutes in Amity Group, which were established by Dr. Ashok Chauhan way ahead. So why I'm narrating this, Dr. Chauhan is a visionary. So he looked at how Amity can contribute to mitigating the global warming, climate change. So that is why these institutes, and we are doing many projects like that, even from Dr. Tanu Jindal, is looking at how does the water pollution percolates down to the groundwater. So she is measuring the leaching of these pollutants going through these different layers of the earth. Similarly, we are looking at restoration of the natural springs for restoring the climate change, mitigating the climate change. We are member of the NASA AirNet. So we are looking at the global monitoring of the environmental pollution, particularly the air pollution. We are looking at green energy, sustainable agriculture. So all these are efforts which Amity is now doing in a modest way. We will certainly augment with the efforts of Dr. Tanu Jindal and the whole group, Dr. Madhupatyaya and other mentors. Now, final message I want to convey is, let us make a behavioral change, because ultimately we have to bring you can have n number of policies, n number of rules, regulations, but ultimately people have to comply with that. People have to implement them. People have to take the initiatives. So the first and foremost will be a behavioral change in all of us. That is the foremost. We should discourage or ban CFC, ozone depleting agents, and the whichever gadgets which we are using. It should be free of this. We should look at the alternatives for the CFCs and other ozone depleting gases and the substances. And finally, we must ensure that the Mother Earth gets healed. This is what is the message I like to convey. And whatever Amity can do, we will certainly, not only in terms of capacity building, but also in research and development endeavors, we will bring such innovations which will help to solve this or mitigate the problems. So thank you, Tanu Jindal, for once again this opportunity to share some few thoughts with all the participants over here. But you spread this message everywhere, because all of us are ambassadors of whatever we learn here. We propagate among our colleagues, institutions, students, parents, everywhere in Amity. Similarly, all the other participants, wherever, whichever responsibility you hold, that let us bring this consciousness, let us bring this awareness across all the society, the 7 billion people. We should create this awareness so that we will be able to restore this ozone hole which is depleted. Thank you so much.
Thank you so much, sir, for your valuable time and your inputs. Yes, indeed, we are now Earth and Environment Climate Change Cluster, and earlier Global Warming Climate Change Cluster. We have done a lot, and we have tried to bring scientists from various campuses, faculty, who are all working in this area. I think it is a small gesture again to work towards, ozone hole filling and how we can contribute by reducing the ozone hole depleting substances, spreading awareness. Thank you so much, sir.
Thank you. Thank you.
Thank you, sir. We want to express our profound gratitude for the exceptionally informative session on this topic. The future will go up in smoke in no time if we continue to neglect it. Protect ozone today and save yourself from a doomed future. With these words, I would like to invite our next speaker, Mr. Rolly Costamo. Sir works as a secondary secretary, Finland Embassy, New Delhi. Sir has pursued master's degree in administrative sciences with specialty in psychology of leadership from University of Lapland. Sir is a civil servant working in the field of diplomacy and interested in politics and economy. Also keen to observe and learn about human mind and social dynamics in global context. Welcome, sir.
Thank you very much. Namaste. Dear students and scholars, First of all, I would like to thank Amity University for inviting me to participate in this webinar. It is a great pleasure for me to be here with you in the context of the World Ozone Day. Today's topic, Montreal Protocol, fixing the ozone layer and reducing climate change, is of utmost importance. Let me introduce myself. My name is Rauli Kostamo and I'm from Finland. I have now completed 2 years in incredible India and it's great to be here. I arrived to Delhi from my capital Helsinki, where I worked with European Union Common Foreign and Security Policy at the Ministry for Foreign Affairs of Finland. Now let's talk about why we are here today. I must say that I'm very humbled to be here among such a distinguished group of high-level scientists and academics. So my approach is broader political, and I hope I won't make you sleep at the end of the day. This year Ozone Day is held under the theme of Montreal Protocol, fixing the ozone layer and reducing climate change. Climate change and depleting ozone layer are real global problems. They pose an existential threat to humanity and ecosystems all over the world. It is a global problem that can only be tackled by working together. Addressing climate change is a huge challenge, but also a huge opportunity. We are at the critical crossroads. We know that climate change is already undermining sustainable development in many different ways all around the world. We also know that those who are already most vulnerable due to their gender, age, disability, or displacement will suffer the most. Science, equity, and economics demand us to step up climate action urgently at the pace and scale never seen before. The good news is that immediate and ambitious climate action also offers huge opportunities for sustainable development. Firstly, we need to understand that the cost of inaction would be devastating for human welfare. This will allow us to stop seeing climate action as a burden and cost and start seeing it as a vital opportunity and investment in sustainable development. Investing in a carbon neutral and climate resilient future offers a triple reward, avoiding devastating losses and generating economic returns, as well as countless social and environmental benefits. Yet, to reap these benefits, we must act now. The decisions we take today will determine our opportunities and risks far into the future. A global shift to carbon neutrality and climate resilience means a comprehensive transformation of our societies. We must align all our policies and finances with the effective climate action. We must join forces across all borders and engage everyone in society. Women and the youth are invaluable agents of change for climate action. In this brief presentation, I will address some key facts behind global warming and some risks related to climate change. Then I will target the means how we can tackle the challenge. And finally, I will point out some opportunities that are related to climate change. Dear participants, global warming is a fact. Despite conflicting arguments from some political interest groups, the scientific evidence of human-induced climate change is undisputable. The IPCC, which stands for Intergovernmental Panel on Climate Change, report has already shown that global warming of 1 Celsius degree has already taken place compared to the pre-industrial levels. Moreover, global average temperature is likely to reach 1.5 Celsius degrees already before 2050 if the current trend continues. The IPCC report states very clearly that we need to raise the level of ambition of climate action if we want to limit warming to 1.5 degrees in line with the Paris Agreement. The take-home message of the IPCC report was that even 1.5 degrees of warming will undermine efforts to achieve our sustainable development goals, but significantly less than the 2 degrees warming. So if we want to eradicate poverty, promote health, food security, and access to clean water and energy, and foster the stability of societies and ecosystems, we must urgently step up the ambition of our climate action. And when it comes to the world economy, the World Meteorological Organization estimates that the climate change mitigation to reach the target of limiting the global warming to 1.5 to 2 degrees Celsius above the pre-industrial era would be 20-fold 20 times cheaper than the cost of doing nothing. This is hugely important to acknowledge. What are the risks related to climate change? First of all, warming, once taken place, will persist for centuries or millennia and will continue to cause long-term changes in the climate system, such as the rise of sea level. Coastal flooding, heat waves, and drought with associated wildfires are already taking place, but they are actually getting much worse. Heavy precipitation, causing tropical cyclones, has grown in tropical coastlines, threatening the areas of intense urban habitation. And India's coastline is one of the most vulnerable in this respect. Also, just a few days ago, a coastal town in Libya, North Africa, received a devastating flood. Many lives were lost and homes were destroyed. This large scale of flooding has not happened there before. We see already now how heat waves are killing people all around the world in large numbers. We see glaciers receding, corals bleaching everywhere in the world. And we see the food security for the whole world being put into question. These setbacks hit the hardest the people who are the most vulnerable, like the poor, disabled, elderly, women, and children. Unfortunately, there are more bad news for the Arctic and the Himalayas. The Arctic region is warming up more than twice as fast as the rest of the globe. The ice is melting and the permafrost thawing. Marine ice sheet instability in Antarctica and the loss of the Greenland ice sheet could result in multi-meter rise in sea level. What is worrisome for India, there is a correlation between Arctic ice melting and the Indian monsoons, which are critical for agriculture and growing population in India. The Himalayan glaciers, which are also known as the third pole, serve as a massive water tower for Asia. It forms the third biggest freshwater reserve after the polar ice sheets. Melting of the Himalayan glaciers would be disastrous. The big river systems originating from the Himalayas, like Indus, Ganges, Brahmaputra, and so on, form the life wire for almost 2 billion people here in Asia. That is around 20% of the global population. How the political systems and the civil society would endure. Climate change is also a matter of security. Disruptions in food or water supply, disrupted livelihoods, and the spread of infectious diseases might lead to uncontrolled migration waves. These conditions would have the potential to escalate into political turmoils, instability, and conflicts in receiving societies, no matter how stable their political systems may be. These impacts can seriously challenge the democratic decision-making systems and coherent civil society. The decisive question is, what can be done? The good news is that there is a wide range of adaptation and mitigation options that can reduce the risk of climate change. Feasibility of solar energy, wind energy, and electricity storage technologies have substantially improved over the past few years. Circular economy may provide a part of the answer. Circular economy is a system aimed at eliminating waste and the continual use of resources. It enables us to reuse natural resources, produce less waste, and reduce greenhouse gas emissions from the industry. New measures are needed, especially in areas related to construction, textiles, transport, and food. And I'm very happy that you in Amity University actually are very much engaged with many of these challenges. A circular transition in the mobility, food, and built environment sectors could reduce the pressure on ecosystems while also reducing greenhouse gas emissions by around 50% by 2030 and by 80% by 2050 compared to the levels that we had in 2012. For instance, in the European Union alone, switching to a more circular use of the four most commonly used materials, which are steel, plastics, aluminium, and cement, could cut industrial emissions by more than half by 2050. For Finland, my country, circular economy is a key element in our transition to a carbon neutral and resource-wise society. Our government program places the circular economy in the very core of the economic and competitiveness policy. We are looking at the paradigm shift, moving away from the linear economy based on producing, using, and discarding products, and moving into solution through a focus on behavioral change, resource and energy efficiency, and the closing of material loops. I'm very happy that this behavioral change was already mentioned here by previous speakers. Most countries, including Finland, are too small to be self-sufficient in circularity. Thus, full circularity requires cooperation across borders. As governments, we have to collaborate and create predictable policies to enable business to transform to a circular model. However, we are not winning the battle, at least not yet. The youth, dear students, around the world are calling for action. There is a clear necessity for an ambitious and fast response to climate change at all levels, local, national, as well as global level. The Finnish government takes climate change with utmost seriousness. Our government program aligns our climate policy with the pathway that limits warming to 1.5 degrees. Our national target is to achieve climate neutrality by 2035 and to shift to negative emissions soon after. I believe we are among the most progressive countries in this respect. We will achieve these goals by accelerating measures to reduce emissions and by strengthening carbon sinks, like forests. Climate considerations will be mainstreamed in key policy areas. We will end the use of coal in energy production by 2029 and fossil oil in heating our houses by 2030. We are developing a sustainable taxation roadmap to achieve our climate targets. Our Climate Change Act has been revised accordingly. As an international actor, Finland aims to be bigger than our size. Together with our neighbors and partners like India, we want to pave the way by spearheading new and innovative solutions. The key message, dear students, is that we all must work together to combat climate change. And this is why I'm addressing you this afternoon. This is why I'm here. Dear audience, international collaboration is key to the academic community, which bears an instrumental role in producing relevant and up-to-date data, as well as innovative solutions for climate actions. It is critical to strengthen academia's collaboration with policymakers, as well as with climate action innovators and implementers, financiers, businesses, and communities. Young people have understood the urgency of climate action. The youth's call for low-carbon transition has grown into a global movement for action that knows no state borderlines or boundaries. And these massive cross-national demonstrations have put more pressure on national governments to take serious action on climate change. Decision makers need to listen to the youth carefully and take their demand for enhanced action seriously. Voices of young people must be heard because youth are the true stakeholders in this matter. Dear students, it is first and foremost your future and the future of the generations to come that is at stake. The United Nations Climate Action Summit in New York has introduced the global youth into the arena of hardcore global policymaking. Echoing the voices of youth in national parliaments may have a pivotal role in limiting global warming and giving the human civilization some more time to breathe. But the time for action is now. Then how about Finland and India? Can we tackle the challenge together? Our countries have shared destiny, as both Finland and India have a massive polar ice sheet next to the territory. We need to study and explore this issue jointly. Already some time ago, Carnegie India, in partnership with our embassy here in Delhi and the Office of the Principal Scientific Advisor to the Government of India, hosted a seminar to discuss Finland's and India's engagement in the Arctic. As you know, Finland is an Arctic country far up in the north. This is why Finland is a member of the Arctic Council, but India also is an observer in the same organization. We also cooperate in the Antarctic affairs. Finland and India are both signatories and consultative parties of the Antarctic Treaty. The consultative parties of the treaty held their previous meeting June this year in Helsinki, my capital. The slogan of the Helsinki meeting was "From urgency to action," and it called on the international community to intensify action against climate change and its impact in Antarctica. Concluding the climate discussion, the consultative parties adopted the Helsinki Declaration on Climate Change in the Antarctic, highlighting the global implications of climate change and the need for urgent action to protect Antarctica. In the same meeting, Finland handed over the presidency of the Antarctic Treaty Consultative Mechanism to India. The next ATCM meeting will be held in Kerala, southern India, next year, 2024. We need to continue our joint efforts in the future. Dear audience, climate change is a challenge, but it can also be an opportunity. An opportunity for inclusion and empowering of youth and indigenous people. An opportunity for strengthening the civil society, uniting people, creating innovations, and starting up new businesses. The more the civil society, NGOs, and academia promote the climate action, the more the businesses and the finance sector will seek to find new opportunities to capitalize on it. According to the Global Commissions on the Economy and Climate and on Adaptation, investing in the transition to low-emission, climate-resilient pathways offers immense opportunities and triple dividends of avoiding losses and damages, generating positive economic gains, and delivering social and environmental co-benefits. The world will invest more than $90 trillion in infrastructure by 2030, which is in very near future. And this sum is actually more than the current stock in place globally today. Much of this investment will be done in India and in Asia. Low emission, climate resilient solutions could deliver, or according to some estimate, $26 trillion of direct economic benefits, while also generating 65 million new jobs and combating climate change at the same time. Here, before finishing, I would like to quote Irish writer called Bernard Shaw, who said, "Those who cannot change their minds cannot change anything." Dear audience, evidence has spoken, and we need the academia and youth to set us on the right track towards a fully responsible and constructive global climate change policy. We need everybody on board. Thank you for your attention.
Thank you, Mr. Rowley, and certainly we as an academician, as scientists, we will really try to show forward the path and the policies and the strategies, the technologies, the sustainable practices which are required to combat climate change and also to fill this ozone hole, to avoid this pollution of the ozone depleting substances. Certainly we are working towards that, and I'm grateful for your time and speech. And since Finland is part of Antarctic and Arctic Treaty, I think we are also working in Antarctica. We can go further ahead to give solutions to the society and also for the globe. Thank you so much.
Thank you, sir, for such an enlightening session on carbon neutral and updating us on the role of the carbon pricing and carbon offsetting in incentivizing emissions reduction efforts and achieving carbon neutrality by 2035. Moving ahead with this, we have come to the end of this very informative and enlightening deliberation. At the end, on the occasion of International Ozone Day, we vow to make efforts for the preservation of the ozone layer. We further resolve to be ozone-friendly citizens and promote use of ozone-friendly goods and services. We shall make all efforts to restrict and control the emission of ozone-depleting substance to the atmosphere and protect and save all forms of life on Earth. Now, I would like to invite Dr. Abhishek Chauhan to offer vote of thanks. Over to you, sir.
Thank you, Richa. So, good evening to one and all. It's my privilege to offer vote of thanks and acknowledge each and every person involved in virtual deliberation on World Ozone Day. We are extremely grateful to our Honorable Founder President, Sir, Dr. K. Chauhan, for his blessing and motivation to carry out such important program. Our special thanks goes to Honorable Chancellor, Sir, Dr. Atul Chauhan, and Honorable Vice Chancellor, Madam, Professor Balwinder Sukla, for their great support and encouragement. I would like to thank Professor D.K. Bandopadhyay, sir, Chief Advisor, FPO, Mentor, Amity Institute of Environmental Sciences, Environmental Toxicology, for his views on the subject. Our special thanks to Dr. W. Silva Murthy, sir, President, STIF, Chancellor, Amity University, Chhattisgarh, for gracing this occasion and sharing his views and highlighting solution and sustainable based approach and actions. Our sincere thanks goes to Professor Tanu Jindal, Madam, Director, Amity Institute of Environmental Toxicology, Safety and Management, for her constant support and guidance throughout the preparation of this event. I would like to extend our warm gratitude to all the eminent speakers for gracing this virtual deliberation and sharing us their findings and opinions. We would like to thank our speaker, Dr. K.V. George, Chief Scientist and Head, Air Pollution Control Division, CSIR Neri, Nagpur, Professor Umesh Kulsestra, Professor, School of Environmental Science, Jawaharlal Nehru University, Dr. Anikendra Kumar, Scientist C, Environmental Monitoring and Research Center, IMD, New Delhi, Dr. Rauli, Secretary, Communication and Country Branding, Finland Embassy, New Delhi. All the speakers for the day delivered intellectual talks and share their knowledge and added to our in multiple ways. We are immensely grateful to each one of them. I would also like to thank all the participants, students, faculty members of various institutions, research scholars, and students from our domain. I also thank all the faculty members, staff of Amity Institute of Environmental Toxicology, Safety and Management, and AIS for their support to making this program a successful one. I would also like to thank Dr. Smriti Sukla Richa for nicely coordinating all the lectures. Thanks also goes to our office staff, Mr. Rajat and Mrs. Mariamma Joseph, for their hard work and support. A very warm gratitude to the IT department for providing this best platform to deliberate this virtual program. With this, once again, I would like to thank all of you. Thank you, everyone. Thanks a lot.